Okay, so in the last video, we talked about components. We talked about how to find an x component and a y component for a vector. And we practiced calculating that. We do that using trig, using either cosine, typically, for the x component, and typically sine for the y component. We didn't really talk about why we do that, though. We just kind of talked about how the x component and y component show how far the original vector extends in one direction. The real reason we do this, the reason we put ourselves to all this trouble, is not just so we can do more math, it's so that we can use it to solve a problem. Because sometimes when we go to solve a problem, we only need to deal with one particular component, and the other component is irrelevant. Let me give you an example of that. An eastward moving boat is trying to cross a northward flowing river. So this is similar to another problem we did a while ago. Due to the boat's speed and the river's flow, the boat's velocity is 5 meters per second at 53 degrees north of east. If the river is 200 meters wide, determine how much time it will take the boat to cross the river. So I'm going to sketch this. Here's the river. Okay, it's flowing this way. And here is our boat. Okay, and due to both the boat is trying to go directly across the river, which is, by the way, 200 meters. It's trying to go directly across the river, but it can't because the river is also flowing to the north. So the boat ends up moving in this direction, okay, both across the river and downstream. And that angle, okay, so the magnitude of its velocity is 5 meters per second, and this angle is 53 degrees, okay? Now, because the boat is not moving in either the x or y direction, the horizontal or vertical direction, as seen from this top view, what we need to do is we need to find the components of the boat's motion. The x component of the boat's motion is given through this equation. The x component, I should say, of the boat's velocity. We always talk about components of a certain vector. You can't just say the x component is this. You have to tell me the x component of what? Of the velocity, of the displacement, of the acceleration is this. The x component of the velocity is given by 5 meters per second times the cosine of 53 degrees. Okay, the x component, that would be this one right here. Here's the y component. 53 cosine times 5 is approximately, and I'm just going to round this to 3 meters per second. And if you notice, if it's the x component and we have north, east, west, south, this is our eastward component. The boat is traveling eastward. It's trying to cross this river. The y component, on the other hand, would be our northward component. That's given by a sine theta. 5 meters per second times the sine of 53 degrees. And that, again, humor me with the rounding, is 4 meters per second. And that is the northward component. Okay? Now, one of these components is useful for us in figuring out how much time it takes for the boat to cross the river. The other one is not. The northward component is not useful to us at all because the northward component has nothing to do with crossing the river. It's how the boat moves down the river. The eastward component tells us about how much time it takes to cross the river. The northward component is irrelevant in this case. It has nothing to do with crossing the river. So we're going to focus solely on our x component. If we're trying to find how much time it takes to cross the river, and the boat is moving at a constant 3 meters per second to the east, the x component, as it crosses, then I can solve this very simply. 3 meters per second equals 200 meters over t seconds. I cross multiply, so I get 3t equals 200, then I divide by 3, and I get the time is 66.7 seconds. Now you might say, well, why couldn't you do that with the original 5? Why doesn't that matter? Well, think about the numbers. If I had plugged in 5 here, I would have gotten a different number, okay? That 5 meters per second included both the part of the velocity that was relevant to us crossing the river and the part that was irrelevant, the part that pushed the boat down the river, okay? That original vector did not help us, okay? It had information in it. It was composed of something that helped us, but also something that was not relevant to us, and it would have given us a wrong answer. If we had plugged in 5, we would have got how far the boat, or how much time it took the boat to travel 200 meters in this direction, but that doesn't guarantee that the boat would have been crossed there. It means the boat wouldn't have been all the way across the river at that point. This boat is trying to cross the 200 meter wide river. We need, if we're going to use the 200 meters, that's in the x direction here, that's the horizontal direction, then we need to know the boat's speed or velocity in that x direction. The velocity in the y direction just does not matter. So my example here is just to show you that that sometimes you will need to split something into components. It's not just a little mathematical trick to make you remember sine and cosine. It is necessary in some cases because you will not get the right answer. This is correct. Anything else that you use for the velocity here instead of 3 meters per second, in this case of trying to cross the river, would be wrong. Okay? So sometimes we need to split things into components. Last topic for this video, since a vector can be broken up into components, that also means that two components, the vertical and horizontal component vectors, can be added up into a resultant. Remember, resultant means sum of the vectors. You can take a horizontal vector and a vertical vector and add them head to tail like we have here and get a resultant. Okay, that resultant is just the original vector. So, if the x component here is 15 meters and the y component is 8.7 meters, what is C, the resultant? Well, we're just going to do the same thing but pretty much in reverse. You have the two side lengths this time, the legs of the right triangle. I know this is a right triangle because vertical and horizontal lines, when joined up, always make a right triangle. How do I find C? Very easy. You use Pythagorean theorem. A squared plus b squared equals c squared. 15 meters, please use units and the equation, squared plus 8.7 meters squared equals c squared. 15 squared is 225. 8.7 squared, 75.69 plus 225 is that. We take the square root, and c is 17.34 meters. That is the length of the hypotenuse. But for a resultant, not only do we need to know the magnitude, we also need to know the direction. If you have a vertical component of 8.7 and a horizontal component of 15, you should be able to tell the direction from the x-axis. And the way you're going to do that is look at the two sides that you were given. This side is opposite our angle theta. This side is adjacent to it. The trig function that is opposite over adjacent is tangent. Tan theta equals 8.7 meters over 15 meters. So I get 8.7 divided by 15. I get tan theta equals 0.58. And please make sure you don't just leave this as your answer. This is not the angle. This is the tangent of the angle. How do we actually find the actual angle? Well, it comes with a little button that you also learned how to use on the calculator, the tan to the negative first, the inverse tangent. If you take the inverse tangent of 0.58, you will get the actual angle. In this case, the actual angle turns out to be 30.11 degrees. Okay, so a little bit over 30 degrees. And that is how you can find the angle of a resultant. I alluded to this earlier when we were dealing with distance and displacement, and I said if you want to find the actual angle of the displacement, there is a way, but I'm not going to get into it yet. Now you're expected to know how to do that, okay? It's all about triangles. It's all about what you did in math. So, to summarize, rules for adding vectors using trig, okay? Rules for dealing with vectors using trigonometry. If you're trying to break apart a vector into its x and y components, you use cosine to find the x component. Ax equals a cosine theta. The a's stand for just vector, so ax is the x component of a vector equals the magnitude of that vector multiplied by the cosine of the angle. Sine is similar. The y component of a vector equals the magnitude of the vector, the size, multiplied by the sine of the angle. Okay? These equations are in the reference tables. Creating a resultant vector. use the Pythagorean theorem, if you know the x and y components, to find the magnitude. Remember, Pythagorean theorem is a squared plus b squared equals c squared. And you're going to use inverse tangent to find the angle. Theta equals the inverse tangent of the y component over the x component. Okay? And as a matter of fact, these equations are also in the reference tables. They are right here under, let's see, page 5 of the geometry and trigonometry section. For a right triangle, we're given the equation c squared equals a squared plus b squared, just in a slightly different form than you're used to, and we're even told what sine, cosine, and tangent are all equal to based on this picture right here. So I guess it's not exactly the way that you learned it, but it's pretty much the same thing. And from this, you can determine that the inverse tangent, or that theta would be equal to inverse tan of a over b, or in this case, y over x. All right? So we've gone over how to, in this video, y components are important. We've also gone over how to take x and y components and bring them back into one resultant vector, the original vector. All right? What we're going to do in the next video is actually learn how to add vectors together. Remember, you did this head to tail where you drew the vectors with a protractor straight edge and you actually had to put them head to tail. We're going to learn how to do that process, but we don't have to actually draw anything or measure with a protractor. You can do that entire process using only trigonometry, and we'll do that in the next video. I'll see you later.